So we have discussed about how actually the learning happen, and if you just do in a nutshell, we have seen that we have this, it's a singular perceptron model. So we have these two different patterns, I mean actually four different patterns. What do we have to do? We have to find out basically the line. So this is the unknown function. This is the unknown function which will basically we have to find out. Okay, so we have to find out the free parameters which represent this unknown function. So now let's you see, so these are the learning steps that we have seen to follow, and then we have taken an example and we have seen actually we have discussed about up to two iterations how the weights will change, right? So now let's go for some more examples that we can address with respect with this single layer perceptron model. For example, the first one is the implementing AND function. Why I'm saying this one? Because you see, we it's very easy to write the truth table of the AND function, and you see, if we consider this A and B is basically the features, and F is basically the output class. So, and if you draw the positions of these different combinations of AB in a graph, it will be something like this, right? So since 0 0, I mean 0 0 0 1 and 1 0, both output contain 0, and if you just put them in this particular graph, we will see that these red points are in one side and blue points in another side. So it's very trivial that I can easily draw the straight line. So somehow it's possible that we can utilize a single layer perceptron model by which you can basically identify two different set of classes. Now second thing is that implementing OR function, similar thing, but here is just an opposite. Like we have many 1 and some only 1 0. If you do the same thing, if you put these points in a graph, we will see we have something like this situation. So all, I mean, and we can easily say that we can easily draw a straight line. This straight line is basically found out from the singular perceptron output, right? So this actually the weights, the synaptic weight matrix of the model will basically realize this function, right? So we can easily draw this particular straight line. Fine. Now let's go back. Let's go to the another very interesting problem, that is about the implementing XOR function. If you implement a XOR function, you see here we are going to face a problem, because you see we have some 1 for some specific case and 0 for some specific case. If you draw these points with respect to 1 0, if you just color them with respect to 1 0, you see you will get a situation something like this, right? Now you see, since the class, I mean with respect to class, the points are in complementary positions. If I ask you that draw a straight line that can basically segregate two different classes, it's not possible. You see, it's not possible to draw a straight line by which you can differentiate two different classes, right? Somehow we can say that okay, ultimately straight line is not possible. Maybe I can draw something like this, a line something like this, but it is not a straight line. If it is not a straight line, if it is a non, if it is a, that means I can say it is not a linearly separable problem. And if it is not a linearly separable problem, then we stuck, because till now with single layer perceptron model we were able to define, basically we were able to find out basically a straight line that can basically differentiate two set of classes. So here we stuck. Linearly separable line is not possible. So this is the problem, that single layer perceptron cannot classify nonlinear separable patterns. Okay, so here we stuck. Now what is the solution? Solution is hidden in a very interesting theorem, what we call Covers theorem. So let's dive into the Covers theorem first, try to understand it, then we will see what can be an advanced modeling for this single layer perceptron. So by definition, what Covers theorem is saying? It says that a complex pattern classification problem cast in a high dimensional space non-linearly is more likely to be linearly separable than in a low dimensional space, provided the space is not densely populated. What does it mean? At the first attempt, maybe this line is not pretty clear to you, but let's go through these lines one by one, and let's reread this line again. You see what's given? A complex pattern classification problem. So we have a complex pattern classification problem cast in a high dimensional space non-linearly. Okay, that means the problem is a non-linearly separable problem. From here this clear, is more likely to be linearly separable. So this situation can be converted to a linearly separable problem than in a low dimensional space. That means if you are in some n dimensional space, and in the n dimension actually represents n features, right? We have seen that this in the n dimensional space, the problem suppose is not linearly separable. For example, something like a Zor problem, you can cast it to a high dimensional space to make it a linearly separable, because until and unless it is linearly separable, you cannot apply single layer perceptron. So let's see what is written over here, that let's x denotes a set of n patterns. What is x? You can say x, say set of fruits, that just we have seen in an example in my previous video, that x is a set of fruits and it's set of n patterns. So there is n number of fruits, which is x1, x2, x3 to x10. Fine. And each of which is assigned to one of the two classes, C1 or C2. Just that we have seen, in my previous video. Okay. There are two fruit class, so you can easily watch that. Now, this dichotomy, that is the binary partition, because I have two classes only, of this pattern is separable if there exists a surface that separates the patterns in class C1 from those in class C2. It's very clear. I must need a surface. Now, how this surface look like? I mean, I have to find out this surface first. Now, how I can find out the surface? We can see that you cannot apply a single layer perceptron because I have assumed that they are non-linearly separable. So what I have done, you see what's given over here, that for each pattern, so let's go to this point, for each pattern xi, some fruit belongs to the set, define a vector made up of a set of real valued function phi ix, such that for I equal to 1 to m1. So what is phi written? You see what is written? Phi x is written as phi ix, then actually phi 1x, phi 2x, then phi 1x. It should not be phi I. I'm sorry. It should be phi 1x. It should be phi 2x. Okay, like so that means you had a point. So I assume that you have a set. Here we have this point which is denoted by xi. This xi you are actually writing as a phi xi. And what this phi is saying? Phi xi is considered as a vector. This is a vector, right? So this phi xi is nothing but phi 1 xi, sorry, phi 2 xi, phi m1 xi. So that means the dimension of this phi xi is what? Dimension of this phi xi is m1, because I have, this is a point xi, this is another point xi, which is actually came from the same point. But what I have done here, the dimension of this point is m1 dimensions. And it is given that if the pattern x is a vector in an m0 dimensional input space, so that means dimension of this xi is m0 and dimension of this one is m1. And what we have done? We have actually, what is written, you see, the vector phi x, this one is written, the vector phi x maps the points in m0 dimensional input space into corresponding points in a new space having dimension m1. So suppose that you are working in a 10 dimensional point. 10 dimensional space means what? Each and every point that you are representing in that space is of 10 dimensions. Very simple, right? Now, in this 10 dimension, those points or the patterns, whatever you can say, are not linearly separable. So what I can do? I can consider a function phi x that will basically map. Suppose this, in that case m1 is equal to, so in that case m0 is basically equal to 10. According to my example, m0 is 10. And suppose I am taking one more space having dimension 15, so m1 is 15. So what actually we are doing, my intention is, with respect to, by the phi function, that somehow represent each and every point of this 10 dimensional space to some point in a 15 dimensional space, right? And that is what I have said, that the vector phi x maps the point in m0 dimensional input space into corresponding points in a new space of dimension m1. Now we refer to this phi x as the hidden function because this space in real doesn't exist. In real mean, if you consider that you have a training data set consisting of say 100 features, it means that one of the, take any pattern of that training data set, each and every pattern is actually defined by 100 features. If you consider each and every a dimension for a feature, that means each and every point you can say in a 100 dimensional space, and each and every 100 dimension has some value for each and every pattern. Now what I am doing, I can see that okay, in this 100-dimensional space it is not linearly separable. So what I have done, I have taken a phi function somehow. Now what is the phi function? The detail of this I'll come later. But assume that there is a some phi function I have got, and for that, using that phi function, you are able to represent each and every patterns of that training data set of the 100-dimensional space to a 200-dimensional space. So this 200-dimensional space doesn't really exist. What exists? 100-dimensional space exists because in real the pattern is defined by 100 features, not 200 features. And that is why those 200 set of points which are actually representing a single pattern are actually called featured, new features. And that is why that particular 200-dimensional space is called feature space. Actual 100 dimension was input space, but 200 dimension will become a feature space. And with respect to Covers theorem, if you are able to map these 100-dimensional points to a 200-dimensional point, it will become linearly separable. It may not be 200, maybe 150 or maybe 115 or maybe 101. I mean, in a very small, in a nutshell, if I tell you what is the Covers theorem, it says that if a set of points is not linearly separable in n-dimensional space, it can be linearly separable in m-dimensional space where m is greater than n. And now how I will represent this n-dimensional space to m-dimensional space? To do this, what we need is that phi. So that is what I have defined over here. You see, that is what actually defined over here. That this phi function. This phi is associated with each and every patterns of the actual dimensional space. Okay. Anyway, so that means to sum up the Covers theorem on the separability of patterns, you see it basically have two things. I mean, the nonlinear formulation of the hidden function defined by this phi x. Obviously, it's a nonlinear function. It's going to be a nonlinear function because the in a lower dimensional space the problem is nonlinear, where x is the input vector and I1 to m1. Now, I hope you have understood what actually I'm trying to say. And second point is the high dimensionality of the hidden or the featured space compared with the input space, where the dimensionality of the hidden space is determined the value assigned by m1. So how much you are actually trying to how a particular point how enlarge you want to do the space, that depends on you. Okay, so what actually I was trying to say is something like this, that a machine learning problem cannot classify directly a nonlinear separable patterns. It cannot do that. So if we have a problem of nonlinear separable patterns, what we have to do, we have to first convert them to a linearly separable problem. And for that purpose, this phi is present. So you are representing a smaller dimensional space to a higher dimensional space, but don't think that the property will change. The property of the points will not change. And one more interesting point is that, suppose, for example, take a data set of human being. Okay, so human being data set contains, suppose, some features, something like hair color, skin color, height, complexion, and say length of leg, and many more. Okay, many more. And you see, now question is that with respect to these features, if we collect the data of say 100%, and if you see that those 100, that means you have 100 patterns, and each and every pattern is for a human being or for a particular person, and each and every pattern is defined by those 5 or 6 or 10 features. So that means each and every point is basically in a 10-dimensional space. And if you see that this set of points are not linearly separable, what I am saying, that do one thing, you just map it to a higher dimensional space. So for example, say 20-dimensional space. So that means the exact 10 features that you have collected, you are mapping those 10 features to a 20-dimensional space. So from where the other 10 features came? Have you collected from that? No. You have collected only 10 features. So from where the other 10 features came? And this is very much fishy. We don't know the exact feature name. But what actually we are doing mathematically, we are representing your actual feature to some unseen feature space which you have not collected, but because of that your problem become linearly separable. And as soon as your problem become linearly separable, you can apply single layer perceptron from that point. And that is actually what our goal is. So that means this situation actually leads to what we can say multi-layered perceptron. It looks something like this. You see, initially we had only 2 layers. Just forget about the other 2. Just the first 2 you consider. We have seen that it's a single layer perceptron. Now what I have seen, that suppose we have these 3 layers over here, these 3 layers. This is say x1, x2 and x3, and you can see that the problem is not linearly separable in this 3-dimensional space. So what we have done, we have mapped this 3-dimensional space to say some n-dimensional space. So for example, that means say it is say h1, it is h2 dot dot dot, it is hn, where n is greater than 3, generally very greater than 3. So naturally your problem will become linearly separable beyond this particular layer. From this point, the artificial neural network realize this problem as a linearly separable problem, and we can apply the single layer perceptron. But the learning algorithm is not going to be very easy over here. The reason is that here we have many other layers in between input and output layers. So it is going to be little bit I mean, very mathematical and obviously a little bit tough. But we will see it actually in the next day. So we can see that that's why this particular units are called hidden layers, because this is your x. Actually you can say this is your x and this is your phi x, this is your another phi x, and this is your y. Initially you had only x and y. because they were linearly separable. Now when I can find out that it is not linearly separable, the problem are not linearly separable, then we have to apply this phi x so that the non-linearly separable issue become a linearly separable problem. That is the key feature, key idea for about, before we start multi-layered perceptron. So we can stop over here for today. We will see the learning algorithm for multi-layered perceptron in the next class. Thank you.